I guess we'll get started, everyone. I want to thank everybody for coming tonight. The goal of this tonight was basically we wanted to start a conversation about shale gas in New Brunswick, and just looking at it at kind of a more academic perspective tonight, and then tomorrow night we have our political presentation. But tonight, we're looking to kind of keep it more kind of on topic about more of an academic side. It's the Association of Civil Engineering's graduate students that are putting it on. So we're looking at kind of the geological formations and also the hydraulic fracturing. So if any questions that we have, if we could stay on that side. We understand there's a larger issue, the economy, the health impacts, First Nations impacts, and those are, there's lots of social and economical impacts that it's just, the topic's too big for us to get into tonight. So that's why we kind of bit off a small chunk of a larger problem, and hopefully maybe we can, everybody here will get a better understanding of what it is when it comes to shale gas technology, and with respect only to two small part of the topics. Tonight we have two speakers. So Dr. Adrian Park, he's going to speak first on geological formations in respect to oil and gas, and then we have Dr. Maurice Dusseault. He's going to speak in respect to hydraulic fracturing. With that being said, I think Craig's going to introduce our first speaker. And yes, sorry, both speakers are going to present, and then at the end we'll have a kind of a question period, so we'll hold all questions till the end. That'd be great.
Alright, so good evening everyone. Just here today to introduce our two speakers that will be giving their presentations. Dr. Adrian Park graduated with his PhD in geology from the University of Glasgow in Scotland in 1983. His graduate fieldwork was focused in Finland. He's also carried out research in Sweden, India, Czech Republic, focused on how rocks, especially base metal ore-bearing rocks, deform and respond to stress. In 1988, Dr. Park came to Canada to take up a postdoctoral fellowship here at the University of New Brunswick, working in the district of Keewatin in Northwest Territories, which is now Nunavut. Since then, he's worked with deformed sulfide ore deposits in New Brunswick, Manitoba, and Quebec. And around 2005, started research work on the carboniferous basins of New Brunswick and the older rocks of Caledonia, which include the host formations of the oil shale and conventional oil and gas deposits here in New Brunswick. During that time, he was a seasonal and contract professor teacher here at UNB. And from 2007 to 2013, he was actually on faculty of Earth Sciences here at the University of New Brunswick. Now he is self-employed consultant in the Earth Science Education and Public Outreach, and is doing contract work with the New Brunswick Department of Energy and Mines. And following Dr. Park's presentation, we have Dr. Maurice Dusseault. He is a geological engineering professor from the University of Waterloo in Ontario. He holds his PhD in Ontario and Alberta. The research problems that he is tackling include the geomechanics, including thermal and non-thermal oil production, wellbore integrity, deep disposal technologies for solid and liquid wastes, hydraulic fracturing mechanics, which is a big part of what we'll be talking about tonight, carbon dioxide sequestration in saline aquifers, and current projects that he's focusing on are hydraulic fracturing, wellbore integrity and gas seepage, compressed air energy storage in salt caverns, enhanced geothermal energy systems, and deep waste disposal and induced seismicity. So he holds 10 patents. He's co-authored 2 textbooks, 530 full-text conference and journal articles, and has worked as an advisor for the governments of Alberta, Quebec, New Brunswick, and also Newfoundland. So between these two gentlemen, there's a wealth of knowledge, and we're really happy to have them both here to talk a little bit more about the technical aspects surrounding shale gas and hydraulic fracturing. So without further ado, I'd like to invite Dr. Adrian Park to come up and get us started for the evening.
Thanks for that introduction, and thanks, Led, for the invitation. Okay, well, my background in all of this, I'm not a petroleum geologist. My background is that I have studied structural geology, the response of rocks to stress through geological time. And as Greg pointed out in the introduction, about 10 years ago, I started working on the Carboniferous Basin here in New Brunswick from the point of view of how it formed, how the rocks had deformed. And as chance would have it, it happens to include the oil shales that are now the focus of so much interest as a potential shale gas source and play. So what I want to look at tonight is, first of all, a definition of what is conventional and unconventional petroleum. Have a look at the shale gas potential in New Brunswick and some of the background geology. I will touch on fracking because Maurice is going to be dealing with that in far more detail than I could manage. And I want to look at some outstanding issues that arise from a geological background. So I won't be covering issues like groundwater specifically. Well, when we're dealing with oil and gas, we are usually talking about something that is hosted in sedimentary rocks. That's rocks that start out as sediments transported and deposited by moving water, ice, or wind. And usually we're dealing with those fragmental sediments that are produced by erosion of older rock. Now, you've probably seen this classification before. It's the common one used for sediments and sedimentary rocks, used by geologists and engineers, is the Wentworth scale. And across the top, does anyone happen to have a laser pointer with them? We seem to be bereft of laser pointers. Okay, I'm just going to wave my arms. Very big one. Across the top there, you've got a scale in millimeters that illustrates the grain size of a sediment or a sedimentary rock. And it goes over on the left from the very finest clay through various silt into various grains of sand, and then granule, pebble, cobble, and boulder. Again, going from clay, silt, sands to gravels. And notice that clays and silts together are mud. Mud isn't just something your children traipse into the house, it actually has a scientific definition. Now, this is what's deposited in a river or a lake or on the coast, or the sea. The unconsolidated material, but what we are usually talking about geologically is these things, which are sedimentary rocks. To get from an unconsolidated sediment to a sedimentary rock, you have to compress it, drive the water out of it, and then cement the grains together so that the rock achieves some sort of coherence. In engineering terms, there's a very strict transition point of one to the other defined in terms of shear strength. To geologists, there's no such subdivision. Unconsolidated sediments are rocks, just like sedimentary rocks. It's a transition. Well, plastic sediments transported by water are the most important from our point of view, and the size of the grains depends on the energy of the water that's doing the moving. The more vigorous the flow, the coarser the material that can be carried, and the bigger the load. And this is a typical depositional environment. The detritus is being eroded somewhere off the top of the picture, and then streams are carrying sediment down into a standing body of water, in this case a lake. It could just as easily be the sea. But the point is, you have a change of gradient as the stream comes down, and therefore a change of energy. And finally, when the moving water of a river or stream hits a standing body of water, the energy drops to zero. There's no flow. So progressively, as these things come down a shallower gradient and then enter standing bodies of water, they progressively drop the heaviest material, the largest grains. So up in the channels of the river up there to the top left, sand and gravel will be deposited in the river channel and then just moved during times of flood. On the delta itself, you'll tend to see a lot of finer sands and silt, And then the very finest material, the clays, ends up suspended in the water, and you'll see these diffuse plumes of mud that can stay suspended in standing water for considerable periods of time. But eventually it will all settle out. But it doesn't all settle out at once or in the same place. You have this sorting of sediment by size. Well, that's in a conveniently arid area, and you don't see any vegetation on top of that. But clearly these kind of environments, where the climate is right, can sustain life on a very large scale. So here's a good example. This is the Mississippi Delta coming down into the Gulf of Mexico. That's the conveniently low energy environment. And again, you can see the general form of the delta at the center of the image, the main river channel breaking up into a series of distributaries, sands and gravels deposited in the channels, finer sands on the delta itself, and then you can see these extensive plumes of suspended clays coming out into the Gulf itself. Now, the delta itself is colonized by a very dense cover of vegetation. So on top of the delta, where you don't have the influence of seawater, you'll see very lush swamp and forest, and this has the potential to create peat, and peat eventually will compress and turn to coal. So those kind of things form on top of the delta. Once you're offshore, the clay and any dissolved salts that are coming down the river are nutrients. So associated with these big clay plumes in the Gulf itself, you often see what they call algal blooms. You're pushing lots of nutrient into an environment where there isn't much nutrient to start with, and the plankton, it's not the algae, they're called algal blooms, it's actually plankton that bloom. They simply go in for a huge population explosion. They've got food in abundance. This is the 12-course banquet. And these creatures go in for this population explosion, they die, they're falling down with the sediment underneath. But the sheer quantity of material coming down prevents effective recycling. And usually beneath these plumes, there's a dead zone. Nothing can live there because the plankton bloom has sucked all the oxygen out of the water body. So instead of the organic material recycling back up the food chain, it ends up on the sea floor. And the same would happen in a lake. Now, so underneath an area like this, you're not just depositing fine-grained sediments, you're also depositing a lot of dead organic matter. Well, what does that become? Just a quick primer for those who are a little rusty on these things. The hydrocarbons we're interested. We are interested in our molecules of carbon and hydrogen. The simplest of them is methane, up at the top left there, 1 carbon, 4 hydrogens. In shorthand, it's referred to as C1. That just refers to the number of carbons involved. Ethane is the next one, 2 carbons, 6 hydrogens. Propane is the next with 3 carbons. The largest carbon chains involve hundreds of carbons. And they all have appropriate names. But notice the shorthand, C1, C2, C3, they're getting heavier with the number of carbons involved. The ones that form chains are the simplest. We can also have them as rings. Benzene is one of the simplest ones. The carbons now form a ring with a hydrogen attached to each of them. That's another C6 compound. As a general rule, these hydrocarbons that are between C1 and C4 are gases at 25 Celsius and 1 atmosphere. So methane, ethane, propane and butane are the familiar ones. From C5 to C25, these are usually liquids at 25 degrees Celsius and 1 atmosphere. And if they're above C25, then they're usually waxy solids. So the heavier the molecules are, the more carbons they got in them, they go from gases to solids through that range. There's one minor complication. There's a range between C4 and roughly C10 where they are gases underground because the temperature's warmer, say 60 degrees Celsius, and when we bring them to the surface, they condense as liquids. They're called condensates. And benzene is often a component of condensates. considered very valuable. Okay, so back to that organic material that was being buried along with the sediment. What we have up here on the right-hand side are three microscopic views of thin sections of rock. These are rocks cut and polished to about 30 microns thickness, so they're translucent. And the vertical side of each is about 3 millimeters. So at the top, we have a sandstone. The grains are about just under 1 millimeter in diameter. The colored ones in the top center are rock fragments, and the colorless ones are quartz. Quartz is probably the most common mineral in sandstones. Now this is a sandstone rather than a sand because the grains are cemented together. And you can see some of the cement, it's that kind of pale brown material. There's a nice patch of it center left underneath that brown rock fragment. But what doesn't show up terribly well in that photograph are the gaps. Think of packing ping pong balls in a bucket. There is no way you can pack them so that there are no gaps left. And sand grains are behaving exactly the same way. Those gaps are the pores. Now, as the sand turns into a sediment, into a sedimentary rock, into a sandstone, cement starts to fill those gaps, but it doesn't fill them completely. Those gaps are the porosity. Think of that as the storage capacity of a sand or a sediment. The other point you'll notice, probably top left, the gaps interconnect in between the grains. That interconnection is the permeability. That's the ability of a fluid to flow between the pores. Think of that as the deliverability of the rock. It can hold a certain amount of fluid, and if it's permeable, that fluid can flow. Now the two slides below are fine-grained siltstones where you'll see that the mineral grains are way, way smaller. Again, the vertical dimension is about 3 millimeters, so those really are down at less than 1/100 of a millimeter in size. You'll still have a porosity in these rocks, and it may still be 10% of the volume of the rock. The difference is the connectivity between those pores is far more compromised. And as they've cemented and turned into a siltstone, that permeability may have closed off completely. So they contain fluids, but the fluid can't flow. Now the difference in those between the upper one in the center and the bottom one, the color is the obvious one. In that central one, there's a lot of organic material. It forms those dark layers at the bottom of the slide, and then it's more dispersed through the rest of it. This is organic material that was buried along with that sediment, and has now turned into something called kerogen. It's a brown, waxy material. It doesn't have a fixed composition, but it's largely made up of fairly complex hydrocarbons. I'll show you an example. That's an example of a component of kerogen, and the center of the molecule is made up of these rings, rather like the benzene ring, but they're all joined together. And this again is shorthand. Where those sticks meet, you have a carbon, and there are hydrogens attached. And you'll see that there are these side chains, like this one here. These are like the propane, butane, methane molecules that we saw earlier on. Now, kerogen is fairly stable until you start heating it up. And when you start heating it up, those side chains start breaking off. Now, one of the carbons may break off and take the hydrogens with it. That's methane. Or a cluster of them may break off, taking the hydrogens with them, and that might be propane or hexane, or one of those light liquids. If you get the molecule hot enough, you'll actually start breaking up the aromatic core, and you'll start releasing much larger liquid hydrocarbon from this solid. So how does the heating process go ahead? It goes ahead as these things are buried and convert from a sediment into a rock, into a sedimentary rock. The graph over there shows it in a fairly crude way. Every different shale or mud rock will show a different profile. It depends on the composition of the kerogen in that particular rock. By and large, they show a pattern similar to that. When the mud is first buried with that organic material, archaea, a very primitive kind of bacteria, are buried with it. There's no oxygen. It's absolutely stagnant. It's like that black, evil-smelling muck that comes up from the bed of the lake when you pull dock in the fall. And those bacteria generate methane. And they can go on doing that until the temperature hits about 40 degrees Celsius. So you can actually bury them drums to kilometre depth. And they're still generating methane. This is marsh gas, and it's produced by the metabolism of the bacteria themselves, the archaea. Now, much above 40 degrees Celsius, the temperature is too high, the bacteria are killed off, and that's the end of the generation of biogenic methane. And at that point, any organic material that's left starts the conversion to keratin. Bury things 2 or 3 kilometers down, and you get them up to a temperature of around 60 degrees Celsius. That's about the temperature of a warm bath. And you start this process of breaking up the kerogen. You start breaking off the side chains. And that generates what's called wet gas. It's dominated by methane, but it contains condensates, it can contain water, it can contain sulfur compounds. Notice there are sulfurs buried away in the aromatic core of asphaltene. Take the temperature up to about 90 Celsius, that's about the temperature of a cup of coffee, and you're starting to break off bigger chunks that are liquid, and that's the light oil. You're still producing wet gas, but now light oil is joined the mix. Take the temperature up to about 125 degrees Celsius, and you start breaking up the core, and that releases heavy oil. This is the same as bunker C, lubricating oils, fuel oil, heating fuel oil. Eventually, if the temperature gets above 150, only small molecules are being evolved, you're back to light oil. Around 160 degrees, everything breaks down to methane. And finally, at around 220 or so, all you've got left is carbon, and that's graphite. You've completely destroyed the kerogen. So, hydrocarbons that are of industrial use, petroleum, that's methane, condensates, light oils and heavy oils, are all generated in that temperature window during burial. Okay, that's cooked up our source rock. How do we generate a conventional oil deposit? Well, that material has to get out of the source rock, which it usually does as the source rock undergoes compression. It's driven out. Because remember, the source rocks, the fine-grained rocks, don't have much intrinsic permeability. Something has to push it out. They then start migrating through suitable permeable pathways towards the surface. Probably 50% of all the oil and gas that's formed through geological time has hit the surface and gone. But from the point of view of the oil and gas industry, enough of it gets trapped on the way to the surface. It hits a layer of impermeable rock that's in a suitable geometry, and it gets trapped on top of a layer of water against one of these impermeable barriers. And there are 2 examples in the lower slide where you've simply got a folded layer that's permeable and porous, and the oil has got trapped sitting on top of water and pores in one of these impermeable aquitars. Another way of doing it is to put it against a fault if the fault plane itself is impermeable. And that's an example of an actual trap exposed in a quarry wall. You can see the arched layer of the aquitard. The area that's not stained is where the gas is present. The stained layer is where oil was present. And further down, below the little character standing next to the oil, you will be into a layer of water, a brine, that's sitting in the pores of the rock. Now obviously the oil well behind is drilling into something much deeper. So to To have a conventional oil or gas field, you need three things. You need a suitable source rock, an organic rich, fine-grained sediment that's gone into that temperature window and has been cooked in the right way so that kerogens release those various kinds of hydrocarbons. You then need a suitable reservoir rock. There's a sandstone shown up there. It could just as well be a limestone. And that reservoir rock has to have a suitable geometry with a cap that's impermeable. And there has to be a suitable plumbing system between one and the other. As with all good comedy, timing is of the essence here. So this is what oil companies spend a great deal of time looking for, and probably of all wells drilled looking for that kind of oil or gas deposit, probably 1 in 20 actually find anything worth exploiting. Well, there is another way of doing it, and this is what's called unconventional oil and gas. Curiously enough, this is the older oil and gas industry. And it dates back to Scotland at the end of the 18th century, where John Cochrane, the Earl of somewhere or other in Scotland, was in financial straits, and on his property in West Lothian, there were oil shales. And his estate manager, a guy by the name of John McIntosh, demonstrated that you could take this oil shale, you could put it in a large kettle, you could heat it up, and a thick, tarry oil oozed out of it. Now, Cochrane decided he would sell the patent to the Royal Navy, and they could use this as a substitute for pitch, as a caulking agent in wooden ships, and as an anti-fouling paint on warships. Well, the Royal Navy eventually decided to go with copper as a way of protecting its ships, and Cochrane was left with a useless patent. However, about 40 or 50 years later, the oil industry in Scotland revived when they realized that not only could you get heavy tar-like substances out of oil shale, you could get a huge range of hydrocarbons if you retorted it correctly. And by the 1850s, there's the Broxburn Oil Works. It was the biggest in Scotland. It was producing a huge range of oil products by mining the oil shale and retorting it. And the lower picture shows you the result. Down in the lower left, these are two-story houses, just to give you a concept of scale. It was mining. They were pulling out millions of tons of shale, retorting it, and dumping the waste. And the waste forms these piles known as bins. The industry died in the 1920s, but the bins are still there, and they're still releasing acid-laced water with an impressive cocktail of heavy metals and arsenic and all sorts of other nasties. They're a major environmental problem. Well, curiously for the Scots, Mackintosh took his patent, realized that if you took canvas and impregnated it with this heavy oil, you had a nice waterproof fabric, and he started manufacturing raincoats, hence Mackintosh. As unusual for a Scot, he didn't realize that the vapor that came off his retorting oil shale could be distilled. Now, given that the Scots have this ability to produce magnificent, magical liquids by distilling vapor, this is a major oversight. It was a Canadian, Abraham Gesner, a doctor from Nova Scotia, who realized that you could distill this material. You could then further refine it and purify it, and you ended up with a light oil that would burn without producing soot. It was a perfect lamp oil. Abraham Gesner probably saved more whales than Greenpeace, because it was whale oil that was the material used for lamps. Well, Gesner was the first government-appointed geologist in Canada. He worked for the government of New Brunswick. And in Albert County, he followed up on a discovery of oil shale and of a hard bitumen that occurs in the shale, something called albertite. Geologists are really imaginative when it comes to naming new minerals. Albert County, albertite. Well, Albert Mines became the site of huge workings that were exploiting primarily the albertite, but also the oil shale. And by the 1840s, these photographs are from the 1860s, it was the second largest settlement in New Brunswick. something like 20,000 people were living there. Only St. John was larger. Now it's 3 farms and Baptist church. And the church was originally built when the mine was operating. It's no longer on the same site. Anyway, this stuff was dug out of here. Gesner and his competitors could never get the financing to build a refinery at Hillsborough. Instead, the stuff was shipped crude down to Boston, where it was turned into kerosene and sold all over North America, all over the eastern part of North America. That's a very familiar Canadian story. Well, what really killed the industry was the discovery, almost simultaneously, at Stevenstown and Titusville in Pennsylvania, and then Petrolia in Ontario, that if you drilled a hole into the right formation, oil would flow out of the ground. No need for mining, no need for retorting, the stuff just came out of the ground. You just barreled it and sold it. Notice there is no environmental impact assessment going on here. It came out of the well, it flowed down ditches into surface ponds, and people scooped it with shovels into barrels and shipped it out wherever they could. The Canadian view is a little more orderly. Well, the unconventional direct exploitation of shales fell by the wayside for the better part of a century and a half. For the simple reason, you made a bigger profit pulling oil out of conventional reservoirs. Everyone knew, or geologists knew, that there were huge potential resources of oil and gas in shale rock. It was getting it out at a profit that was the problem. Well, all that changed in the late 1980s when in the Barnett Basin, whoops, I can't quite reach that, but it's down there in Texas, it was demonstrated that you could drill one of these gas-bearing shale horizons and you could extract gas at a profit by employing 2 new techniques. Horizontal drilling, where you drill a standard oil well and then turn the well underground and follow the layer of shale. And secondly, large volume slit water hydrofracturing, about which my colleague will be saying rather more. The Barnett Shale has now been exploited for about 25 years. But this suddenly opened up the whole of the North American shale-bearing basins to exploitation. For instance, in the Hilliard-Baxter-Mancos Niobrara area, otherwise known as the Green River Basin in Utah, it had long been known, like since the 1880s, that there was probably as much oil locked up in those shales as occurs everywhere else on the planet. Gives you an idea of the scale of it. No one had ever figured out a way of pulling it out of the ground at a profit. It required too much processing. Well, these are the various basins in North America. Plays that are under development or producing are in red. So we have the Barnett, we have the Eagle Ford, also in Texas, the Haynesville-Bossier in Louisiana, the Fayetteville and Woodford in Arkansas and Oklahoma, and the immense Marcellus, Utica, and Ohio play in Pennsylvania, Ohio, and New York State. Right up at the top, right there, you'll see Frederick Brook. Looks tiny. The point about Frederick Brook, here in New Brunswick, is that by comparison with these shales in the US that have been exploited now successfully since the Barnett was broken open in the late 1980s, the Barnett, Eagleford, Haynesville, Fayetteville, Marcellus, they're only 100 meters thick at most, but they cover a very large area. The organic content is generally quite low. Parts of the Marcellus are only 4% total organic carbon. Frederick Brook doesn't cover anything like the same area, but in places it's over 1 kilometer thick. And its total organic content averages around 8%. The highest measurements are actually more like 16%. So what the Frederick Brook lacks in area, it makes up for in sheer volume. So let's home in a little more closely. This is the basin that contains it. It's called the Maritimes Basin. Most of it lies under the Gulf of St. Lawrence and between Newfoundland and Cape Breton. But it comes on shore in New Brunswick and in Nova Scotia, and it's at depth underneath Prince Edward Island. It formed largely during the Carboniferous. That's between 360 million years ago and 300 million years ago. And don't bother too much about the details. From our point of view, there are two important layers within this sag that's filled with sedimentary rock. And that's at the bottom here, the Horton group, in the oldest part of the Carboniferous, and then various shades of rather pukey green up at the top there, which are the Pennsylvanian rocks. The Horton group contains the Frederick Brook oil shale. And the Pennsylvanian rocks up at the top contain coal. Coal is also a potential source of methane. But we're going to concentrate on the shale and where it lies on the Frederick Brook. That's where it sits in the column. As I said, the details are not too important. Using the same colours, this is the extent of those rocks on land in New Brunswick. The Pennsylvanian rocks you'll see are the most extensive. They're the various shades of rather putrid green. And then the various browns and reds and blues are the older ones. Notice the dark coloured Horton group. This is where they're at the surface. We have the area of oil shale that was known by Gesner, and that's over in Albert County on the Petitcodiac estuary towards the centre right and Hillsborough. And you can see there's patches of it at the surface. There's a stringer of it at the surface down through Rosevale to Elgin, a much larger surface exposure to the south of Sussex, and then more to the north of Sussex, and another little patch up there indicated as Indian Mountain. Now this area has been explored and mapped and drilled for this oil shale since the 1860s. We have a very good three-dimensional appreciation of where the shale is, how thick it is, etc. The area that hasn't been explored to anything like the same extent is that whole central top right area where we see Pennsylvanian rocks at the surface, and we suspect there may be the older oil shale bearing formations below it. Those are the existing oil fields, conventional. Stony Creek, that was discovered in 1910 and was producing oil and gas until 1991. Contact Petroleum went back into it in 2003 and it's producing again. And then the conventional gas field at McCully, discovered in 2000, and it's been producing again for just over 12 years. Areas that have looked promising underneath the Pennsylvanian cover. The Marysville subbasin just to the south of Fredericton here is not looking quite as promising as it did. We now suspect that there's no Horton down there. There's an area near Minto, but the two areas that are most promising are up around Dopetown and of course over to the top left there in Kent County around Wishibokto. Now one reason these places have looked promising is because we've known for a long, long time that there are methane seeps, natural oil and gas seeps at the surface. Anywhere where the Horton group, that dark brown, is at the surface, a bedrock well is likely to contain methane. There are water wells in the Sussex area that people have been able to ignite since first European settlement. It's a very good idea if you have a bedrock water well in any of those areas to have it regularly checked for methane, if you don't want what's known in the aviation industry as a spontaneous disassembly event. Think about that. Areas again where there's been methane in water wells, a survey carried out in the early 1980s identified Kent County as an area where methane bubbled up in water wells, suggesting there's something underneath. Now that could be the coal in the Pennsylvanian rocks, It could be Horton Group underneath, or it could be the local swamp. Methane can come from many places. Well, this is the exploration lease map for New Brunswick. Corridor, who operate Macaulay, have that small lease just to the south, just to the north of Sussex. In the Elgin area, they are now the sole owners of the lease Apache have pulled out, where they're carrying out tests of the oil shale directly. Contact owned the Stony Creek lease, and then in that paler brown, Swing have taken exploration leases right across that Pennsylvanian swathe. They're taking the biggest risk. They're going into virgin territory on the suspicion that there's something there. Well, this is the area best known, just showing where the shale is at depth. Again, we're dealing with the Fredericton Brook in the Horton Group. The dark brown is where we see it at the surface, as on the other map. The sort of olive green is where we know it's present at depth because we drilled it. And the pale green is where we suspect it's at depth. We know there's Horton, we just don't know it's Frederick Brook because the characterization hasn't involved drilling it. We don't have ground truth on it. But we suspect it's there. What do these things look like in the third dimension? Well, I'm going to show you some cross sections that are marked on this map. There's one A to B in the Hillsborough area, there's one C to D in the Sussex area, and there's another one G to H, which runs in the opposite direction from Sussex to Petticodiac. Now, these cross sections are produced by a combination of drill hole analysis and seismic reflection analysis. The topmost section shows the Hillsborough area, going from A to the north and B to the south. You can see where the Horton comes to the surface near Albert Mines. That's where the old mines were. And it's present at depth underneath the Hillsborough area. And over on the left, you can see the position of the Stony Creek oil field. It's in sandstones within the Horton Group, sourced by shales within the Horton Group. They've been buried to the point where they're giving off light oil. That light oil has migrated into a sandstone reservoir. The center section is the Sussex area. Again, you can see that great thick swathe of Horton Group at depth. The position of the Macaulay field is located directly above it in the center there. And notice the vertical scale. It's the same on all of them. I'm too short. But there we are. Don't try this at home. That is a kilometre on vertical scale. So you can see the thickness of that unit underneath Sussex is of the order of a kilometre. G to H goes from Sussex to Petticodiac, and you can see that the section, the great swathe of Horton in there is over a kilometre thick. And that's the whole oil shale, but a substantial part of it, probably 70% of it is. And the Macaulay, the location of the Macaulay field is also shown on that section. Okay. How much gas or oil is there likely to be there in the shale? That's ignoring the conventional reservoirs, but how much oil and gas could be pulled out of that oil shale at a profit? Well, the current reserve estimate, and a reserve, bear in mind, a reserve is the amount of gas believed to be there that can be extracted at a profit. It's not that it can't lose profit, it's just so much interesting rock. It will stay there. Current reserve estimates are in the region of 2.3 to 2.4 trillion cubic meters of gas. If you're more familiar with the American way of reporting these things, multiply by about 40, and you end up with 80 to 90 trillion cubic feet. That's a substantial amount of gas. It's not as big as the Barnett, or the Marcellus, or the Woodford, by those big deposits down in the States. But in terms of the New Brunswick economy, it's a big volume of gas. That is based on the reports that Corridor and Contract Petroleum issue to their shareholders. Now, this is done according to the due diligence of the Securities and Exchange Commission on the New York Stock Exchange. All that means is that if an independent auditor comes in and looks at their numbers, they'll arrive at the same answer, with an error. In other words, you're not simply pulling a number out of your rear end and throwing it in front of the public in the hope of attracting large amounts of money. That is called fraud. But bear in mind, those numbers are based on the corridor lease and the contact lease. And you saw from that lease map that those are quite small areas of the shale. So in terms of the total shale, we don't know. If we're going to convert a resource, which is simply the amount of gas down there, into a reserve, then you have to figure out how much of it can be pulled out as profit. And profitable recovery is the key to that transition. That leaves us with a number of geotechnical issues that are outstanding. Firstly, the fact that the Frederick Brook has a high kerogen content is great for its potential to yield gas. But if you're fracturing it, the rock has to respond to what you're doing to it in a brittle fashion. You have to produce cracks to enhance the permeability. If you can't do that, your rock is too plastic. It's like trying to fracture chewing gum. And the higher the organic content is, the more likely the rock is to be plastic. In engineering terms, it's got a lower plastic index. We don't know this. Well, we don't know that parameter well enough to be general about it. Presumably, Contact Petroleum and Corridor have done the studies on their lease. We also know that the Frederick Brook contains swelling clays. Usually between 2 and 4% of the rock is swelling clay. Once they're in contact with water, they expand. The whole point of fracturing the rock to increase the permeability means that you're increasing the amount of water in contact with that rock. Swelling clays have the potential for closing off permeability as fast as you're creating it, if water is used. Again, this is a parameter that's we're very unsure about. The other thing is, if the kerogen hasn't matured enough, you can fracture the hell out of it and nothing's going to happen. There's no gas to release. It hasn't matured to that point. Now, clearly at Stony Creek and McCully, that maturation has happened. But for much of the basin, we simply don't know. Well, with unconventional oil and gas, the problem is getting the gas out and getting it out to profit. In the 19th century, this involved mining. The bins of central Scotland illustrate that there were major environmental degradation problems involved with that. In the 21st century, this involves fracking. And I'm going to leave Maurice to say far, far more about fracking. So I shall. What I will show you, though, however, is that fracture-induced permeability, increasing the permeability of the rock, is a very old practice. And I'm showing you this because it's one of my favorite photographs. This is fracking around 1900. It might have been Hillsborough, it was probably Dover. It may even have been Stony Creek. But spot the health and safety violations that are pictured here on the left. These gentlemen are pouring nitroglycerine down the borehole. The guy with a very steady hand is pouring it into the funnel, and the funnel is touching the inside of the pipe so that this thick oily liquid will run down the pipe without dripping. If it drips, it will detonate. They look to be about 1 gallon cans, 5 litres. There's enough nitroglycerine down there to take out downtown Fredericton. The detonation involved letting everything run down the hole, and then one of them would drop a pebble down the hole, and they would run like hell. The explosion would happen a kilometre or so underground, induce fractures in the surrounding rock, and improve the flow of oil. That was the hope. We've come a long way since then. This is modern hydrofracturing using water. Maurice will say a lot more about this in his presentation. What I will say something about is three of the causes of concern that arise from all this. Surface leakage and contamination. Hydrofracturing involves large volumes of water. The water that comes back from the process may contain hydrogen sulfide, heavy metals, radioactive materials, and there's been a lot of concern recently about earthquakes said to be induced by hydrofracturing. Well, water storage and disposal in New Brunswick, in the draft regulations, hydrofracturing water cannot be stored in open ponds. It has to be stored in tanks. That reduces the risk of surface spillage. It doesn't eliminate it, but it considerably reduces it. However, what do we do with the water once it's been used? Even if it's recycled, eventually it has to be disposed of. The province currently has no treatment and disposal facility. The production water from Macully and from Stony Creek was traditionally shipped to Divert in Nova Scotia, where it was filtered to remove the hydrocarbons. If you can filter sewage, you can filter hydrocarbons. What you were left with was a brine, about 3 times as strong as seawater. No heavy metal problems, no radioactive problems. It was diluted down to seawater and then released into the Bay of Fundy. Divert no longer takes New Brunswick water. Currently, it's being shipped in tankers by road to a facility in Quebec. The flowback water in New Brunswick, well, hydrogen sulfide has never been an issue. We've been working these oil shales now since the 1840s, and they generally do not release hydrogen sulfide when they're processed. The oil and gas that comes out of Macully and Stony Creek is referred to as sweet. It doesn't have this toxic gas in it. As far as the heavy metals go, the test wells at Elgin, where hydrofracturing was carried out, had very low concentrations of arsenic, cadmium, mercury, and lead, and no uranium. Radionuclides, uranium in the Frederick Brook and in the Frederick Brook part of the Horton is actually unusually low. Uranium in the geological environment usually has an affinity for organic material. And for some reason, the organic material in the Frederick Brook has not soaked up uranium. As one of my colleagues put it to me when we were discussing this about a year ago, she's a biologist. She just said to me, "This is the kind of thing that keeps you awake at night, isn't it?" I said, "Yeah, unfortunately." We know this because there's been 2 major uranium exploration programs in New Brunswick over the last 40 years. The only uranium showing that's actually in the Frederick Brook is to the north of Moncton, and it's 1. The Marcellus Shale in Pennsylvania, which has a major radionuclide problem associated with it, this should have surprised no one, because back in the days of the Manhattan Project, and in the early 1950s, the Marcellus was actually prospected as a uranium ore. In places it runs 5% uranium oxide. So it's not surprising that the flowback water contains rather unhealthy amounts of radium. It's a decay product of uranium. That should not be an issue in New Brunswick, but it's something to be monitored and something to be made aware of. Earthquakes. This has been an ongoing debate now for 3 or 4 years, and it was made far more acute in 2011 when a couple of small earthquakes happened in northwest England. This is my home ground. I grew up in this area. And just near the town of Blackpool on the coast, you can see where it says 2011 quakes. there was a test hydrofrac being carried out in carboniferous shales in that area, and there were 2 small earthquakes. Now, Greenpeace UK made a big deal of this, claiming this was more seismicity than had ever happened before in an area where there was none. The spots show earthquakes recorded in this area over the last century. It's one of the most seismically active parts of the British Isles. They took that off their website very quickly. In terms of the largest earthquakes recorded in this neck of the woods, one near the town of St Helens down there happened about 40 years ago, and then one marked as M3.7 there in 2009, magnitude 3.7, magnitude 4. They'd shake the pots. They might crack the plaster. They'd definitely wake you up. Most of the rest of them are below magnitude 2.5. You wouldn't feel them. You need instruments to detect them. And the 2 that happened near Blackpool were 1.7 and 1.9. Some locals claimed to have heard something, which is distinctly possible because these earthquakes were very shallow. They were only 2 kilometers down. Now, an earthquake of that magnitude at that depth, you may well hear. It's unlikely to actually feel them. I'll point out this cluster over here that are all about the same size as the quakes near Blackpool. These are right underneath the city of Manchester. 3.5 million people live there. Those are associated with old coal mines. The locals call them bumps. And again, you tend to hear them rather than feel them. In other words, there's no danger to life and limb. There's no danger to property. Earthquakes are unnerving if you've never felt one before, but these are not catastrophic events. The British government has brought in draft regulations for hydrofracking where they've introduced the concept of acceptable levels of seismic activity. In other words, any industrial activity, whether it's hydrofracturing or the deep injection of wastewater, which can also induce seismicity, as long as they don't induce seismicity higher than what is normally occurring, it should be acceptable. Particularly in an area like this, where there's a lot of seismic activity, but none of it constitutes a hazard. Okay, I think at that point. Other issues are basically well integrity, wastewater disposal and treatment, the nuisance, the heavy plant involved in hydrofracturing. But these aren't geological issues. These are issues of regulation and enforcement. In other words, they are engineering and political issues. So as an audience largely of engineers, I do a 25-yard punt. Over to you guys. Thank you.
Saskatchewan has a very healthy heavy oil industry as well. So remember that those provinces are familiar and happy with oil and gas development onshore. Not so much Newfoundland. Not so much Newfoundland. I'm sorry, I'm speaking like somebody from away, Newfoundland. I've been corrected a number of times. Newfoundland. So it turns out that the shale oil prospective area is down in the southwest corner of Newfoundland. And all along the coast are oil seeps and little oil pools that have been known for centuries. The First Nations and subsequent explorers and fishing vessels from Portugal and Spain and France would actually gather the pitch from these little seeps and use the pitch for whatever reason, probably, as Adrian said, sealing their boats. Okay, so that's down in that region, and of course offshore. I just kind of sketched the outline of about 15 months ago. That moratorium is being re-examined at the present time, and activity is on to try to evaluate the potential issues that arise in hydraulic fracturing in southwest Newfoundland. Well, the issues that arise in hydraulic fracturing in southwest Newfoundland are not different from the issues that arise in hydraulic fracturing in shale gas or shale oil development in other places like Pennsylvania and Ohio, New Brunswick. Remember, there's no onshore oil and gas wells that are producing in Newfoundland, but there are about 130 in New Brunswick. And there's about 150,000 producing oil and gas wells in Alberta. So the rocks in southwest Newfoundland and the rocks here in New Brunswick are not the same exactly as the rocks in Ohio and Pennsylvania and Texas, but those, but it's the same kind of physics for fracturing. We do the same things in Texas as we do in Pennsylvania, and I'm sure the same things will be done if the shale gas industry ever develops in New Brunswick. So, Dr. Park punted the ball to me as an engineer. And of course, I'm going to kick the ball down the road to the politicians. Right? I'm not a policy person. So we try to collect and analyze and parse the information in such a way that we get a better understanding of the physics. And as academics, we do that for the public. That's why we publish things. It's called publish. There's a link there, I assure you. And it's our responsibility to try to help clarify and understand the risks. So a lot of engineers these days are doing risk assessment, quantitative risk assessment. There are a number of studies being done on quantitative risk assessment associated with the oil and gas industry in various parts of North America and the rest of the world. I'm involved in a little wee bit of this in the area of well integrity, for example. I want to point out that all industrial activity carries risk, but the risk is not necessarily additive. In other words, if we do something new, does it mean we have more risk? Let me give you the example of Nova Scotia. Nova Scotia obtains 56% of its electrical power by burning coal, the worst of the fossil fuels. Just a one-to-one comparison of the amount of energy that you can get per carbon atom. In natural gas, you can get, or per carbon dioxide molecule rather. With natural gas, you can get twice the amount of energy per carbon dioxide molecule that you emit as you can from coal. So that means per kilowatt hour, you're putting out half the carbon dioxide if you use natural gas for electrical energy. And by the way, that's the reason that Quebec Hydro is having some economic issues right now, is because before the shale gas revolution in Pennsylvania and the northeastern United States, they basically set the price for their electricity. Shale gas in the United States is replacing coal at a remarkably rapid rate. It's cut the coal consumption by 40% in about 8 years. And guess what? The price that Quebec used to be able to command isn't there anymore. Now they're not price setters, they're price takers. The utilities in the northeastern United States are saying to Quebec Hydro, you're gonna have to drop your price or we're gonna put in some natural gas plants, okay? And Quebec has. So for the first time in the history of Canada, Quebec is talking to Ontario. That's astounding. They're saying that, would you be interested in a little bit of electricity at a reasonable price? You know? I'm serious. This is what's happening. So that it has had an impact. The shale gas industry has had an impact all across North America, big time. By the way, The Economist magazine, which does a list of most livable cities in the United States every year. By the way, in most livable cities in North America, of the top 10, about 4 of them are Canadian, but that's another story. But in the United States, the most livable cities 5 years ago was the most livable Portland, Oregon. Now, which city do you think was voted the most livable city in the United States last year? Anybody know? Pittsburgh. Steel Town, the Rust Belt, right in the middle of shale gas country. Shale gas has created a boom there that is unprecedented, actually. I go down to Pittsburgh a couple times a year, and it's a really, really nice city. We've got a couple of fabulous universities there, Carnegie Mellon and University of Pittsburgh, right downtown. Boy, and it's a really nice place. All right, the bottom point is here, though, that decision-making has to include many non-technical issues. So if it was just simply a matter of energy and cleanliness, the Nova Scotians would say, oh yeah, let's develop some shale gas and get rid of that filthy, dirty coal, which has tailings ponds, accidents on trains, mining accidents, it emits sulfurous gases, it emits mercury into the air. None of those things is emitted by natural gas. But no, Nova Scotians have said, we want a moratorium, we don't want any shale gas development, we're happy with coal. We're happy with coal. For 45 years, my wife has been trying to tell me that decisions are not made on the basis of logic and science. I'm beginning to believe her. Beginning to believe her. I'm not advocating that the Nova Scotians develop their shale gas if they don't want to. That's their choice. Right? Saying that, at least in the short term, replacing coal with shale gas has had major beneficial environmental effects in the United States. But of course, we don't want to hurt the homeland. This is the ski hill here just out of Corner Road. Anybody been skiing there? Yeah, it's a really cool place. I was driving down that highway in a blizzard in January to go give a talk about hydraulic fracturing, and I got yelled at in the talk. That's okay, I'm used to being yelled at. My wife's only 5'1", but she's got a big voice. No, I think she's as gentle as a lamb. But you know, this is very close to shale gas country, and you're going to, if you're living there and you don't have a job that is in that industry and you're secure, well, shale gas development or any kind of development doesn't really carry a great attraction. You know, for example, here's an example of traffic in Pennsylvania in the Marcellus Shale development, and that's a big issue. The heavy traffic that Adrian mentioned is one of the, and you can see up at the top there stockpiles for casing. All right. So the fact, and there are many issues. I just chose traffic here. Shale gas development and ACEGS stands for multi-stage hydraulic fracturing. After we fracture at a whole number of points along the wellbore. Yeah, it involves heavy equipment that has to move along roads. That is called traffic, and we know the risk as engineers remarkably precisely. We can, based on statistics, we can tell you how much risk will be engendered by increased truck traffic. That's very good. The question is, can the risk be reduced? Let me give you an example. In Pennsylvania, the hydraulic fracturing operations now, which would require many trucks, you'll see an image of one later on, the companies go and discuss when convoys can go through communities. They promise no trucks on the road during school bus time or during commuting time. So, say on a Monday, you know, they'll pick up a phone, they'll phone the sheriff, you know, in Squareville, and they'll say, we've got 20 trucks, can we bring them to the town tomorrow at 10 a.m.? And the sheriff will say, 10 a.m., you're going to be here on time? Yep, okay, fine. He shuts down the town for 10 minutes, the convoy goes through, the risk has been reduced dramatically. Okay, so we can manage these risks. That's what engineers do, is we try to manage the risks. The question on the bottom is, do the benefits outweigh the risks? That's not my domain, that's a policy issue. That's a policy issue. The people in government and their advisors have to weigh the benefits and the risks of any kind of an industrial development. reactor at Point Latrobe, whether it's building a chemical plant by the Irving family, undoubtedly, somewhere in New Brunswick. So these are all issues that carry risks that have to be evaluated. And if shale gas is ever developed in New Brunswick, the risks have to be understood. Exaggeration of the risks and misinformation is not helpful, but good science and quantification and engineering are, because that can allow you to make informed decisions. So, what are the facts about shale gas and multiple stage hydraulic fracturing? I can't tell you all the facts tonight. I'm just going to give you, as we say, a kiss and a promise. How does it work, and what are the likely impacts on the Earth's surface? Risks. Are there the number 7 bullet or 6 bullet? Are there risks in not developing a resource? Okay. In other words, is there a socioeconomic penalty that can be associated with not developing something? Remember, Canada was built on development of things, not resisting all development. I am, as an engineer, almost by nature, pro-development. I'm not pro-shale gas. That's your decision. But development got us where we are. And we can't probably go into the future just by writing apps for iPhones and selling them to each other. Well, Adrian talked about earthquakes, and you might be surprised that the largest earthquake, the second largest earthquake ever recorded in Alberta by the year 1970 was in Snipe Lake, in an oil field that was being water flooded by injection of huge volumes of water at fairly high pressure to try to sweep the oil to the producing wells. And that's where Snipe Lake is. Okay? The rest of the dots are the magnitude of earthquakes that have been recorded in Alberta from 1922 to September of 2006. And I trust you're not too surprised to find that they are in a belt in front of the mountain range. Well, 10 days ago, Friday last week, a magnitude 4.4 took place at Fox Creek, right there. I believe, I may be wrong, but I believe this may be in the top 15 or 20 earthquakes ever recorded in Alberta, maybe in the top 10 even. Down the spot of the top 10, but the Snipe Lake earthquake was bigger. Induced seismicity. So, my colleague down at Western University, Gail, and this is yesterday, by the way, posted on this website. It's the website that misquoted me. David Coon here is aware of this story. They interviewed me by telephone, and then they cut out every single phrase that I said that was a qualifier. It's unfortunate, but you can't say no. So Gail was asked by this gentleman, Andrew Nicofora, and basically Gail is a scientist, and her conclusion is not too surprising. We have to study this, and we have to answer questions about how big, how often, how deep, what is the relation to injection, what are the surface effects, and I'm going to describe to you this MMI, which is called the Mercalli, Modified Mercalli Intensity Index. Because all you hear about in the press is 4.1, 3.2, or like Adrian said, 1.7 and 1.9. It doesn't really mean that much, because a 4.4, 10 kilometers deep, cannot be felt probably by anyone, but a 4.4, 3 kilometers deep, is widely felt. So the magnitude, which, you know, the Globe and Mail and the Telegraph and the Courier Times, they all say, a magnitude 4.7. The reporter has no idea what that meant to the surface. But nevertheless, they do that, okay? Baseline data. And I'm working in this fabulous area of Colorado for the American government. And they have the world's deepest and longest operating saline water disposal well. It's been disposing of saline water at 14,900 feet, which is about 4.2 kilometers. for 22 years, and it's been monitored seismically for that entire time. And if any of you are interested, I can send you some fabulous papers and even link you to these people. It's the world's largest database on induced seismicity from well injection, and it's the biggest earthquake ever generated by this was 4.4. Here's one in northeastern BC 30 years ago, 4.3. So what does that mean? As I said, not much. But I'm going to show you the map of the Snipe Lake intensity in a moment. This is the modified Mercalli's intensity scale, NMI. And number 3 there is felt indoors, hanging objects swing, like a chandelier or a hanging plant. You'll notice it's swinging a bit. Vibration like the passing of light trucks. Number 4 is windows, dishes, and doors rattle. Snipe Lake was larger than the event 10 days ago. So let's show a Mercalli intensity of Snipe Lake. The Mercalli has not been done yet for the Fox Creek one. So here's the Snipe Lake. Mercalli index, not felt, 2 to 3, and in that central area, it's 3. Okay, 2 to 3, or 3. So, the largest induced earthquake, which is greater than the one that happened 10 days ago, had a Mercalli intensity of 3, no damage. The earthquake in Paradox Valley on January the 28th, 2013, that really caused some consternation, was 4.4. Some people say that cracks were created in their walls, in the plaster. That's the only claim of damage. Nobody even claimed that a dish fell off a shelf. I'm not saying that it's pleasant to be woken up by a 4.4, but it is not damaging if it's occurring from hydraulic fracturing or injection, apparently. Okay, and there's a lot of studies. This is in the Groningen, actually, they pronounce it Groningen. Is there a Dutch person in the crowd that can pronounce that correctly? Only a Dutch person can pronounce that name correctly. In the Groningen oil gas field in the Netherlands, there's swarms of tiny earthquakes happening all the time. All right, let's move on to hydraulic fracturing. This hydraulic fractured zone is what we try to create when we hydraulic fracture at depth. So we have a well bore, some perforations, and we put in some fluid. Fluid might be propane, like Corridor did a few months ago here, a couple of small propane fracs. It might be water, it might be carbon dioxide, it might be nitrogen. The cheapest is water, and they will use that if the rocks are not, say, all full of swelling clays. If the rocks are full of swelling clays, like more than 2% or 4%, then they may have to stick with things like carbon dioxide, nitrogen, or propane, because those don't cause the clays to swell. So let's assume now that we have done our fracturing. I've drawn a vertical well here, but it could be a horizontal well. That's the fracture height and the length and the thickness of the fracture zone is given there on the left-hand side. Now, let me put this into scale. The fracture height tends to be about maybe 100 meters, maybe substantially less. So, if the ceiling above me is the surface of the ground, a fracture at this depth would be about that high. If this was 2 kilometers, 3 kilometers from there. There have been all kinds of claims that fractures can rise to the surface and contaminate the groundwater. There has never been a case of that known to happen yet, anywhere in the world. There are issues in hydraulic fracture. If you don't do it right, you can communicate to another wellbore and have fluids come up via the wellbore. So now, after an incident 2 years ago in Alberta, the government has passed much stricter regulations on it. can have a well where methane may be seeping in from some shallower zones and seeping around the outside of the well, so that the gas is seeping into shallow aquifers and maybe venting to the atmosphere. Certainly there are issues, but the idea that a fracture can propagate from 2 kilometers deep to the surface is not, you just can't, there's just no way it can happen unless there's a pipeline, and rocks are not pipelines, as Adrian showed. So when we do a number of these zones along the axis of a well, that's called multiple stage hydraulic fracturing, and I've drawn 6 of these zones. Usually there's anywhere from 10 to 30 of these zones, depending upon the nature of the rock. So we have these wells that are roughly parallel, and they've got a whole bunch of fractured zones on them. And remember, they're 2-3 kilometers deep. Now, we get a lot of scare literature out, and this is an example of scare literature showing a horizontal well with fractures rising up into the groundwater zone, with the wellhead spewing stuff into the surface. This is misinformation, or maybe even propaganda, depending on how you want to call it. It is not based on fact. It is really wrong. It's uninformed garbage, and I'm being kind. I don't want to call them liars, but it's massively uninformed. I would suggest that you be very critical on anything that you read, including what I write. Maybe especially what I write. Okay? Because if I'm saying that the risks are minor, then you darn well better hold my feet to the fire and make sure they are. I'm an academic and I claim to speak from the pulpit of knowledge, therefore my standards have to be a damn sight larger than the standards of these people that write crap on blogs. I'll do my best to be honest all my life. I may make a mistake or two, be a little bit taller, but we'll do our best to be honest. That's our job. Risks are always a probability of an event times the consequence. So this is up in northeastern British Columbia, where we are having a whole bunch of small seismic events happening, magnitude 2.5, 3, something like that. 1 or 2 of them have been felt at the surface only so far. But that's the surface. This is not Babylon on Lake Ontario, as Toronto is kindly known. My point is that risk is not just a probability, it's also the consequence. So if we have earthquakes of magnitude 3.5 under Toronto, all political hell will break loose. If we have earthquakes of magnitude 3.5 in the Horn River Basin, which is in northeastern British Columbia, there are no known consequences. Whoa. Well, I see. I probably went to the website there. Average population density is 1/20th of a person per square kilometer. Wait till you meet this very thin person. Actually, probably the oil industry goes and hires all of these people to be environmental assessment engineers. Don't get me wrong, the oil industry does exactly that. Everybody, the lady on the plane, her husband, she's coming for the 50th birthday of her son, who's a professor of chemical engineering here, Ryan, I think is his name. Maybe some of you know him. Anyway, she said that I was working on my slides, and she said, "Is fracking really bad?" And I said, "Not quite as bad as you hear." She said, "That's what my son says too." Boy, he had a great plane ride. But she did say, "What about all the water you need for fracking?" Well, actually, it turns out that in terms of a place like New Brunswick or Nova Scotia or British Columbia, it's not an issue. The amount you need is very, 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 very small considering what's available. If you're in the middle of Australia, and by the way, there's a great big prospective shale gas basin called the Amadeus Basin, right squat in the middle of Australia underneath the Gibson Desert. Water is an issue there. Here in New Brunswick, not so much. Do we use beautiful little marshlands water like that? Not an option. Not permitted. Do we use groundwater? High quality groundwater? Not an option. Not permitted in areas where there's any possibility of doing that. So these are risks that are easily managed. It's called no. That's how we manage this. Adrian mentioned tanks. All of those tanks lined up on the left there. I have failed to count them. I should one of these days just to show you that I can do that in the slides that I've seen. I didn't make it, so I stole it there. Borrowed it from Trican. I forgot to put Trican on that, sorry. Somehow got lost in it. Okay, all those tanks they are used to store the hydraulic fracture flowback liquid that comes back after you fracture. About 40% of your liquid will flow back to the surface, and you have to put it in these tanks. This is not the United States, where they do allow it in lagoons. And Carrie, groundwater specialist, will probably tell you all lagoons leak. It's just a matter of how much and when. Now, you see a whole bunch of frac trucks all lined up there, and there's about 10 of them, and in the middle is the yellow thing there. That's where they're actually fracking that one well. And if you know where to look on the diagram, you'll see about 10 other wells that they're going to frack, one after the other, one after the other. It's a very big industrial operation, and this size of industrial operation has many people in New Brunswick scared. They don't want the trucks rolling down the road. That's policy issue. What happens in the United States is not what happens in Canada. Please don't take cases in the United States and accuse the Canadian regulators of allowing this to happen. We are much more cautious in the way we regulate. However, I'll say it politely, accidents do happen. I can say it more pronounced, for sure. But accidents do happen. And that is a piece of casing with a wellhead on top of it that ruptured about 20 meters underneath the ground because of high pressure. When something gave way, flew through the air and landed on top of the truck. Nobody was hurt because you don't allow people in close to a fracturing operation. If you want to take your life under, if you want to risk your life and limb in an industry, I would recommend fishing, forestry, and agriculture, the three most dangerous industries in Canada. Oil and gas comes, I think, number 8. Relatively low risk to life and limb. If any of you have ever worked in the oil industry in the last few years, then you know that everything is about safety. Here's the impact of 2 wells drilled in the McCulloch field. And these are wells that have been hydraulically fractured. Well, not massively, but somewhat. And now they're fenced off, and the gravel pad is in the process of being rehabilitated with vegetation. If you drive around Calgary, you'll see that the impact on the environment is not very large. Did anybody see Bill Nye, the science guy, last night on CBC? No, I guess not, because he appeared on TVO, which is just Television Ontario. That's kind of our public station. And he was talking about how the land is devastated by oil and gas development. Well, I suggest you drive around Calgary, Red Deer, Edmonton, and most of Alberta, and see that it's not devastated. People who live with this in their backyard. But again, things can happen. This is a leaky well about 10 years ago in Ontario. Okay, the leaky well was identified and fixed. The regulatory bodies demand that oil companies and gas companies put up money in advance in a fund to fix wells. If, for example, an oil company goes bankrupt and no longer can afford to, these are called orphan well programs. Yeah.
We know what the rail industry does, because they're often
you have no choice in Alberta.
No, I know, but I mean, recently there was that derailment in
Miracmichi.
yeah. That was, a lot of that was traced back to the fact that even the cleanup effort, there were no funds diverted specifically for those.
Right, no, it's United States Oil and the United States owner of a railway.
Yeah, but it was Canada than that.
Hey, get on their goddamn ass and make sure that they have a big enough insurance policy, for God's sake.
Well,
That's a regulatory issue, and I feel pretty strong about that. Get the damn insurance policies in place. We call these bonds. When a company is transporting an oil that can be volatile, they better have a big bond.
But
And we failed to force them to do it.
Yeah.
So now the railway is bankrupt and is being sold, and I don't know where the money's gonna go. And that's a tragedy. It is. We have ways of avoiding or mitigating the tragedies, or at least paying for them, if we use them right. And that's the importance of development, is to have a reasonable regulatory policy in place.
But how can we ensure that that actually occurs?
Well, if you can't, then you shouldn't develop anything ever. I'm serious.
No, I don't.
If you cannot, as New Brunswickers, establish a regulatory environment for an industry, then don't even go there. Don't even go there. Alberta has a regulatory environment, so does BC. But if you feel insecure as a province, then you shouldn't be developing.
What if that security comes from a false place?
From a false place? I'm sorry, I can't answer that question, but maybe Sam?
I
I'm
suppose
just wondering if we should let the speaker finish and then.
Yeah. Save that thought, okay? I'll try to get through really fast, I'm taking too much time.
I suspect the one is for tomorrow anyways.
Yeah, actually, a lot of it is for tomorrow, I have to admit, it's policy. Okay, is hydraulic fracturing a dangerous technology? Actually, it's not. Compared to many other technologies, it's actually very low on the danger scale in terms of life and limb. And the number of accidents that have happened where fluids have actually come to the surface and into aquifers, we know of two for sure in Alberta. Alberta has 450,000 wells, of which about 40% have been hydraulically fractured. Okay. I'm not saying it doesn't happen. It does. But it is extremely rare, and it's almost always when the hydraulic fracture fluids are connecting to a close by well that was not identified properly. So the Alberta regulator has put into place regulations forcing the company to identify all the nearby wells and to monitor them continuously during hydraulic fracture. Those regulations were passed in August of 2014, just about 8 months ago, in response to an incident that took place in about a year previously. So the regulatory system is responding very quickly. All processes involve some risk. What's the risk of 56% of your power coming from coal compared to replacing it with something else? It doesn't have to be natural gas. Why is it that we seem to be able to live with the risks of coal-fired power plants? Just because we're familiar with them. The risks in hydraulic fracturing are about 100 times larger from things like surface spills of chemicals, leaking tankage, improper storage of chemicals. And those are the kind of things that you have to have heavy regulatory hand on. Chemicals have to be stored safely. We've been handling chemicals for 100 years, and Dr. Bessner here is a chemical engineer who has all his life been dealing with the storage of chemicals, and he'll tell you how heavy the regulations are. Same regulations for the hydraulic fracturing industry. More if necessary, heavier regulations. These risks are manageable. But the genuine concerns are methane emissions. But again, you can't go off and claim that it's a huge problem. You have to compare to others. I'm going to quote some numbers that I'm quite aware of, and I'm not doing this facetiously. It's an issue for comparison. There are 3.6 million head of cattle in Alberta. The bacteria inside their stomachs is a variant of the archaeobacteria that Dr. Park was talking. They turn cellulose, grass, into their cell walls, and they excrete methane. On average, 105 kilograms of methane per head of cattle per year. It is estimated that that is many times larger than the amount of fugitive methane that is leaking from wells and pipes in Alberta. Many times larger. Don't screw with my barbecue. Okay, that's what somebody said to me once when I pointed out that that is a major source of methane. Long-term wellbore integrity, we have to do better. Issues related to the intensity of development, like traffic and stuff like that. These are all issues. I don't have an answer, but I think that the bottom bullet here, we need a science-informed decision-making. Decision-making should not be based only on emotional response. We have case histories. People have been speaking very, very loudly in New Brunswick about the contamination of water, well water with methane. Well, in Pennsylvania, which has about 400,000 wells just in Pennsylvania, the groundwater has been contaminated with methane for all time, well before the oil industry ever started, because that whole belt, the organic material that Dr. Park was talking about, has been slowly seeping methane up to the surface. It's very hard to drill a well in the Appalachian belt of Pennsylvania without having methane in the well. Now, we're not talking a few wells. We're talking a few million farm wells. If methane was a toxic agent, there would be a huge health problem in Pennsylvania. We can take that as a data point. I'm not saying there is no issue. I'm saying that exaggeration of an issue cannot help us make decisions. Well contamination is a possibility, and it has happened, and it will happen, and it's an issue. But it's not the same as E. coli in your drinking water, which killed 7 people in Walkerton from an agricultural operation some 10, 11 years ago. But it is a huge development scale, and because the Frederick Brook is so thick, the Frederick Brook is ever developed. There will be quite a dense development scale, and that's something that has to be considered. So the reality is that fracking itself doesn't interact with the surface. Well bore integrity is an issue. Small seismic events will happen, absolutely, for sure. Standard industrial accidents will happen. We always try to keep those to a minimum. The industry now is required to do full disclosure of all fracturing chemicals by law in New Brunswick if they fracture. Canadian regulatory agencies all across Canada are tightening up their rules on shale gas development and massive hydraulic fracturing. And water use is gradually becoming a non-issue because the companies are learning how to use salt water as a fluid as opposed to fresh water, and also to recycle the flowback of the fractured fluid time and time and time again so that they don't accumulate large amounts of waste fluid. You have no social license to frack. This is a picture of, it's close to McCully gas field. A friend of mine took here recently. Frackers are not welcome. Even if they're your sons that are coming back from Alberta. But, sorry, that's too sarcastic. I'm trying to understand shale gas and shale development quantitatively, and so far, I've been surprised by the massive hostility, and I think it has to do maybe with the increased level of disbelief or mistrust in corporations and governments, a lack of faith in government, and not founded so much on factual numbers of risk assessment as founded on an emotional response to large industry, large government trying to impose something upon a local community. That is a social policy issue that I don't want to get into because I don't know much about it. Okay? I think you're entitled to an opinion, everyone is, but I don't think that you really are entitled to misrepresent facts or to lie or to just cherry pick. You've got to look at the whole picture. If natural gas replaces coal, few people in the world would say that that is bad. Most people would say that that is good. Misinformation, however, is rampant, and I also claim that misinformation is a risk. Fracking does not kill. So misinformation represents part of the whole assessment of risk. So I'm going to skip the last conclusions because I've kind of said this again before. Just thank the New Brunswick Energy Institute for the opportunity to come down here from Waterloo today and speak with you. I have no political or social agenda to push. All right. I do not belong to any party, and I don't even want to admit what party I voted to in the last election. You would be shocked. You would be astounded. And I'll try to answer any questions I can as honestly as I can. And you'll please forgive me if I sometimes make a little bit of a sarcastic remark in a vain attempt at humor. But